In this video, we're going to be talking about normal distributions. Specifically, we're going to be looking at what makes a normal distribution unique, and then we're also going to look at some characteristics of and numbers associated with the normal distribution, and then we're going to use it to solve some pretty basic questions. Part 2 of this video is going to get into the types of problems that involve using the standard normal table, which is part of your book. So we're going to start first of all by saying, what's a normal distribution? Earlier, we've already talked about the fact that a density curve has two properties. It has to sit on the horizontal axis and be on it or above it, and it has to have an area equal to 1. I could have that density curve take the form of a rectangle. For example, a rectangle that has a base from 0 to 4 and has a height of 0.25. That would be a density curve. A density curve could also have a different type of shape. It could be skewed and sort of form a smooth shape, but definitely have a longer tail on one side or the other. This particular graph certainly wouldn't have a very high height. It would probably have a height somewhere in that neighborhood of 0.25 again, but it might have a longer base, depending on how the area is distributed. But the type of density curve we want to focus on is symmetric. It is also mound-shaped, and it has a single peak in the middle. It also, to be normal, has to have some very specific properties in terms of how its area is distributed. And so rather than trying to draw a bunch of really poor normal distributions, I'm going to import some as pictures because they're going to look a lot better that way. In its most basic sense, this is what a normal curve looks like. Notice that it has that perfect symmetry left and right. It also has a peak at 0, and then it has a scale that runs along the bottom axis there from approximately -3 to +3. You can also tell, though, that on the ends, the curve seems to continue outward along the axis. In fact, the curve continues out infinitely, and there's always just a little bit of tail left. But once you get beyond about 3 or 4 standard scores from 0, the amount of area that's left in that tail is so small as to be essentially insignificant. Okay, so if I were to then look at this picture in greater detail, what I'm trying to find out is, what can I say about it, or what properties does it have? Well, the first thing I want you to notice is that if I draw a line from -1 or +1 straight up to the curve, I create a center part in the middle that's also still symmetric. The point where these two lines intersect the graph here and here are actually unique points. They're called inflection points because at those points, the curvature of the graph changes from being concave up to concave down. That's how we can help locate that point, in fact. If I draw another line at -2 and a line at +2, as you can see, I'm sort of carving my graph into these vertical slices. And some of those slices are, in fact, the same. If I draw a line straight up from 0, I can definitely say that what's on the left and right-hand side of that are definitely equal slices. For a normal distribution, these particular vertical slices each has to have a very specific area. Let me bring in another picture, and you can see what those areas are. These two photos show you two different ways to consider the area under a normal curve. On the picture on the right, you can see the vertical slices that I created on our original picture, and notice the area that's in each one. What we would say is that this vertical slice right here contains 34% of all the area underneath that curve. Remember that the area underneath the entire curve is equal to 1, so I could also express the area in this piece as 0.34. This little section in here is approximately 13.5%. So it would represent 0.135. If I wanted to find the area of both of these pieces together, all I would have to do is simply add those two numbers together, and it would give me the total area for that region, which would be 0.475. So I can combine different sections together through some really basic arithmetic. Another way to look at it is what's shown over here on the left, and that's really what you're going to hear about mostly, which is that if you go one standard deviation on either side of the mean, which is sort of this section that's right in here, that's going to represent 68% of all area. So a vast majority of the area is going to be located within 1 standard deviation of the average. But we've kind of heard that before. Within 2 standard deviations of the average, you're going to find 95% of all data. And within 3 standard deviations of the average, you're going to find 99.7% of all the data. Where's the remaining 0.3%? Well, it's out in those little tiny tails that I mentioned before, but it's so insignificant as to not even be worth mentioning. So these normal distributions get used for a variety of things. But one of the things that's important to remember, because you'll start to see them sort of everywhere, is that they definitely don't get used for everything. What I'd like you to do next is take a look at the problem on page 137 of your book. In that particular problem, what we're going to be looking at is how we could use the normal distribution to solve a problem. You want to stop the video and read problem 24, and go ahead and also read problem 25. We're actually going to work our way through both of those, and we're going to start just by drawing and labeling a picture, and then we're going to continue onward to use that in number 25 to answer a question. So when you're trying to draw a normal curve, that can be a difficult thing to do. What you want to try to do is make the curvature appear to be concave up, meaning it sort of curves up on the left-hand side and the right-hand side, but sort of goes concave down in the middle. Just try to make it so your curve doesn't look like a U. Other than that, do the best that you can. It's not easy to draw those curves. I wouldn't say I'm very good at it. In problem 24, you're given the fact that we have the heights of American men, which is approximately normal, with a mean of 69 inches and a standard deviation of 2.5. Now in your book, you'll oftentimes see that notation given to you like this, with a capital N, and then you'll also see numbers given 69 and 2.5. The N indicates we have a normal distribution. The 69 is the mean, which you may remember we're going to denote in this particular case by mu, and sigma for the standard deviation. So if you see that information given, it's trying to give you a lot to look at it all at once. Now that means that if the mean is 69, that's the number we could label right in the middle of our distribution. The other thing you want to do is be able to say, well, I know at the sort of the end of the distribution, I essentially have 3 standard deviations. So I'm going to make 3 hash marks, the third of which is right at the edge of my graph. I'm going to make 3 hash marks on the other side, getting to the other edge. And now essentially to know how to label those, all I'm going to do is take 69 and add and subtract 2.5 appropriately to figure out what's going to go where. So my first increment to the right would be 71.5, then 74, then 76.5. Subtracting from 69 will get me 66.5, 64, and 61.5. So for problem 24, we've essentially done what we needed to do. We drew the curve, we've labeled the axis across the bottom, and we've put numbers that are all appropriate according to the mean and standard deviation. So now the only thing that we want to do is when we move on to problem 25, we're going to use this graph as best we can. So let's look at number 25, problem A. We're going to use our curve to answer it. It says, what % of men are taller than 74 inches? Well, that would mean that they fall into this portion of the curve, meaning that they're between the second standard deviation and the third standard deviation. I'm going to bring that picture back in so we can see how much area is in that strip. So you'll notice in this particular picture I imported here to the right, between the second standard deviation and the third standard deviation is about 2.5% of all data, so we would say the appropriate answer there is 2.5%. And that's basically all we have to do. We're simply reading area from the graph. How about we take a look at part B? In part B it says, between what heights do the middle 95% of men fall? Well, if you remember, 95% is what is between 2 and -2 standard deviations. So on our picture over here, that would be between 64 inches, that's the 2 standard deviations on the below the mean, to 74 inches which is 2 standard deviations above. And that's all we need to do to answer that particular question. Problem C. What percent of men are shorter than 66.5 inches? This is a similar question to what we saw before, it's just a different area. So now we're looking at these bottom 2 sections added together on the graph, these 2 right here. So we're going to take 2.5% and 13.5%, we're going to add those together, and we're going to end up with 16%. Last but not least, D says a height of 71.5 inches corresponds to what percentile of all adult American male heights? Well, 71.5% is here. And so basically what I want to know is what is the area below 71.5? That's going to be our percentile. So we would have to add together a few different pieces. We have to go back over to our picture here and say, I want the vertical strip starting right here, because we're 1 standard deviation above the average, all the way to the end. We're going to add all of that together. So we're basically going to get the 16% in the tail, plus the 68% in the middle, however you want to add that and however you want to think about it. But essentially, that's going to be 84% is in that range, so it's at the 84th percentile. Now, all of the problems we just did are using a relationship that comes from this basic picture that I imported right over here. The rule that we're using when we employ this picture has a name. It's called the 68, 95, 99.7 rule, which simply says how we're carving up all of these pieces into little slices and combining them together. So when you're trying to solve a problem, you can invoke that rule. Sometimes you're told to use it, which simply means make a good sketch, label the axes, and then you should be able to answer questions without doing a whole lot more than just addition and subtraction. The next video, we're going to look at some questions that are a little harder.